This is part 3 of section 2.1. We will construct truth tables for more complicated statements. So first of all, what is a statement form or proposition form? This is just an expression made up of statement variables such as like those letters and logical connectives. So far we have these. And then it becomes statement when actual statements are substituted for the compound statement variable. So when you replace PQR with actual statements, then it becomes a statement. Otherwise, it's called statement form. And for instance, this is a statement form, okay? And the truth table for a given statement form displays the truth values that correspond to all possible combination of truth values for its component statement variables. Like here, we are going to construct a truth table, and it consists of all the possible values when you have those possible combination of the true or false values from those variables. Let's first begin with finding the truth table for the exclusive OR. Earlier, we say the exclusive OR means P or Q, but not both happening at the same time. So if we translate this directly into statement form, this says P or Q, right? Or Q. But if you can recall what but means and. But means and, by the way, P or Q. But means and, not both, right? Not both, that means not happening at the same time, like P and Q are not happening at the same time. So not P and Q. So this is a statement form or symbolic form for the exclusive OR. So if I was write P or Q, but means and, not both. So not P and Q happening at the same time. Now let's construct truth table because we have only two variables. I'm going to list these two variables, P and Q, here in my header. And we do already have agreement. So when we construct truth table involving two variables, we'll have 4 rows. So, and then the combination will be like that. The first one is true, true. Next one is true, false. And then false, true. And the last one is false, false, right? So we'll have 4 rows. And now, draw 4 rows. Probably should have prepared a table for you, but I did not. Okay, now, and then what are the columns that we need? What are the columns that we need? Take a look at what we are going to have. We need to find the truth value for this operation. And because it's inside the parentheses, that should be done first, right? So that's the first operation. And similarly, this is co-equal, like they have the same priority. They are both inside the parentheses, but I'm going to just label that as 2. Okay, so the second one. And now we are left with the and not, the not, these two connectives. And if you can recall, not has the first priority above the and. So this should be done the third, and the very last one should be done. This is the last one should be done. Now, oftentimes, the book has this tradition, like you list all the operations that you need to do. So P or Q, that's the first one. And then the second one, second column, I'll create another column, P and Q, which is the second one. And the third one is the not, P and Q, right? So the third one. And the very last one is just the whole P and Q. P or Q, I'm sorry, and not, P and Q. So that will be it. This sometimes can be a little redundant, a little tedious, to be honest, but let's do that step by step, is especially when we are doing the at the beginning, okay? So like this is the first one. So this is my first one. This is an OR. This is an OR operation. If you remember, OR is only false when both are false, right? Otherwise, it's always true. So I can quickly do that. And the second one is the AND operation. The AND is only true when both are true. So therefore I know that it's true here and then false everywhere. The third one is the negation of this parenthesis, which is the result of the second one. So basically you're negating this column. So therefore when you have true, this becomes false, the negation. When you have false, this is true. When you have false, this is true and true. So the negation of this column. Now the very last one is the AND of the result from the first one and the result of the third one. So basically, you're looking at the AND operation of this column and this column, right? So we're going to look at the AND. You know, for AND, it is true when both are true. Otherwise, it will be false, right? So therefore, we are going to look at this will be false because there's a false there. So this is false. And this is true, so the result is going to be true. And this is true, so the result is going to be true. And the very last one, because there's a false there, is false. So for the exclusive OR, it will be true. It will be true when one of those is true. It's false when they're both either both false or both true. Okay, so that's the truth table for the exclusive OR. Now, sometimes I feel like that's a little kind of too many columns to write. So sometimes I prefer to write it in a more condensed way. So sometimes I may write it this way. So I'm going to do a little demonstration here. So in this example, we have 3 variables. Therefore, we have 3 columns for each column for each variable, and we have 8 possible combinations because this is 2, 2, 2. So 2 each, 2 possibility for each. So 2 times 2 times 2 is 8 possibilities. And we are going to do this true, 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 false, true, false, true, true, false, false, and so on and so forth. This is usually how we do it. 3 true or 4 truths, 4 false. True, true, false, false, true, true, false, false. And here this is alternating. Now, there are only actually 3. So, but this one should be done first because it's inside the parentheses. And which one is the next one should be done? This one should be done the next, the negation. And this one should be the last one. Okay, so obviously, if we don't have a too complicated statement form, not too much we need to write. We just add another column, but sometimes I do this. P and Q parentheses or not R because we identify this is the first one to do. So I'm going to look at P and Q column and then just write the results, the truth value for this P and Q underneath this and connective symbol. So it's true when both are true, right? So therefore, I know that these two are true. And then otherwise, it's false because none of the other ones are true at the same time, right? That they're both true at the same time. So therefore, it's false otherwise. Okay. And the second operation is the not. So this is the not. So not R, I just find the negation of R. We just alternate that again. So false, true, false, true, false, true, false, true, which is the dark blue column. And the third one is, I'm going to use the purple. Third one is the OR. This OR is the OR of these two results. So I don't look at here anymore. I just look at this red column and the dark blue column, and then find the OR. The OR is, it's only false when both are false. So I just skim through. Do I see any both false? So this is false, and then this is false, and this is false, right? Only these three rows, they are both false. Otherwise, it's true. So usually, and this is my final answer. This column is the final one. So sometimes I do that, but if you have more complicated statement, this can be like the word can be condensed a lot. So just that FYI, okay? I'm gonna move this back to somewhere here just to keep the work. But now I certainly want to also show you the how it is supposed to be written. And take a look at, we have this first operation. So we want to find a column for P and Q, okay? And then you see the next operation, which is the not R. So you want to form a column for not R. And the very last one is gonna be a P and Q parentheses, or not R, P and Q parentheses, or not R. So I suppose you, because we have gone through that, I suppose you should be able to finish that. And the very last column should be the same as this column. So I'm going to skip that and then leave you a little extra after class assignment to fill up that. Now let's use this truth table. Let's take advantage of this truth table to determine the value, the truth value of this guy when P is true, Q is false, R is false. That means this. Let's look it up. P is true, Q is false, and then R is false, which is this row, right? P is true, Q is false, R is false. And if you remember, this row is, this column is the final result. It's the last operation. So the answer is going to be true. The truth value is T, not the false. Okay. So in general, you've seen that table with 2 variables, 3 variables, and 1 variable. So if the compound statement involves n simple statements, then we should start with the table with how many rows. You can pause here and think about it, and the answer actually is 2 to the n. You multiply to n times. So if you have 3 variables, 2 times 2 times 2 is 8. So 2 cubed is 8. If we have 2 variables, 2 times 2, which is 2 squared, which is 4. Okay. All right. Last topic is, let's talk about the logical equivalence. Let's define R as it rained and S as it snowed. And consider the following 2 statements. Let's translate both into symbolic form first. That means statement form. It is not true that. So that means not true. That means not, right? That tells me, hey, the rest of that is a whole part. So it rained. That means R. Or it snowed, right? S. So all means it snowed. And it did not rain and it did not snow. Did not rain means the negation of R. So here this means not R. And that is N. It did not snow, so it did not snow. So not S. Okay, not S. Now let's construct truth table for both. So I'm gonna, because we have 2 variables, only R and S. So I should begin with 4 rows. Okay, 4 rows. And the R, let's say true, true, false, false. Here, this is true, false, true, false. And the first one is like not R or S. The second one is not R and not S. Well, sometimes I prefer to condense my writing, so therefore I'm gonna use my little small the way that I used right here, because I feel like this probably should not be it should be easy to follow here. So take a look at the first statement form. Let's identify the parentheses. So I should do this first, right? And then I'll do this after finishing the first. And for the second one, there are two nots, one and. So if I label this is my first one, this is my second one, and this should be my last one. The end should be done the last. Okay, so let's do those one by one. So for the R or S, so it's or, it is only false when both are false. So in other words, only this one is false, otherwise it's true. So maybe I'll use a red. So this is false, otherwise it's true, right? And let's change this to a different color. Okay, and then after that, I should negate this result. That means I'm gonna negate the result from the first step. So therefore, I have negates true, which is false. Simply negates this guy, right? Negates each one of those. So this is false, false, true. Now take a look at so down the first one is the result. This column that represents the result, the truth value of statement form. Let's take a look at the second one. So the first operation is to negate R. So I'm going to negate this column. It's in the red color. It's going to be false, true, false, true. Double check my work. And the second step is to negate S. So negates this guy. So it's dark blue. So it's false, true, false, true. And the third step is to find the and, which is the conjunction of these two results. So these two columns, because it's and it's true when both are true, false, otherwise, right? So therefore, I'm gonna look at well, I actually find a sorry, when you're watching my video, you probably catch my mistake here. When I negate R, for some reason I was reading, I don't know which column I was reading, but negate R, let's negate R. False, false, true, true, right? That's the negation of that. So I'll correct that. False, false, true, true. So you gotta be careful. This is one example of not being careful here. Now, lastly, this is n of these two columns. It's true when they're both true. So these two are the only true at the same time. Otherwise, it's false, right? Okay, so that means this column and this column, they're the final result. Okay, let's compare them. Let's compare them. Do you see that they're identical, right? You see that they're identical? Same truth values, right? They have the same truth values. So when this happens, we call these two statements, they look different, but they have the same truth value. We call them logical equivalent. They're logical equivalent. And this actually is called, so we actually have this result. Do you see that? That's the result that we have. That's the result that we have. Not R or S, not the R or S is equivalent to not R and not S. So if I apply that, this is going to be not P and not Q. So this all becomes M. This all becomes M. And here's another important result. If it's not of the P and Q, this will turn out to be not P or not Q. So the M becomes or. Here the or becomes and. So similarly, the and becomes or. You in your homework, I think you will prove this. And how do we prove that? We actually just prove this result, right? So you have to construct truth tables. And what about not P? I hope that this is pretty intuitive. The double negation, you get it back, right? It's just P. And the last two results is called the Morgan's law. These two, the Morgan's laws, they're very useful, and we'll be using that all the time. And let's apply the Morgan's law to some statements. Say, Tony will have a burger or a sandwich for lunch. So do you see that I have two statements here and connected by a or? So this is a Tony will have a burger or Tony will have a sandwich, right? So if you think of this as your P and this is your Q, this is all, this is all. So you have a P or Q statement. How would you negate it? So you're gonna negate P or Q, which is this guy, right? So the negation of P or Q is gonna be not P and not Q. So which means Tony will not have a burger. Tony will not have a burger. And then also you and at the same time, right? Because it says and Tony will not have a sandwich. Will not have a sandwich for lunch. Okay, so that's how you apply the Morgan's law in this case. Now let's take a look at the next one. Luke will stay late for homework tonight, and he will be late for class tomorrow. If you see that there are two statements and stay late for homework tonight, and the connective is and. He will be late for class tomorrow. So this is the and statement. How do we negate it? How do we negate it? It will be not P or not Q. So the and will become or. So I'll say Luke will not stay late for homework, right? Or become or. He will not be late for class tomorrow. So this is how you are gonna negate this statement. Now, what about the last one? The last one, again, I would certainly encourage you to pause the video and think about it first. Sometimes when you have this problem, you can even graph and then find the negation. But here in logic, I encourage you to write it out and do it step by step. So this inequality we can say that x is greater than -2, and at the same time, right, x is less than or equal to 5, right? So the n is the connective, and we're going to use this version. The n will become the O after you negate. So the negation will be, it's going to be not. You're going to negate each one. Negative x is greater than -2. And this change to or the not x is less than or equal to 5, right? Now, not this case. That means x is, this is, if you read this, how about I just -2 less than x. That means -2 greater than or equal to x. Or sometimes I read x less than or equal to -2. This becomes and. So this is x greater than 5, right? So x is, yes, x is less than or equal to -2 and x is greater than 5. If you graph that, x is -2 is here, 5 is here. So that means this part, right? And if you draw the original inequality here, -2 here, and oops, and 5 is here. And the original one was like less than, oops, I'm sorry, it says all. Sorry about that. Oh, well, I'm gonna, so I'm sorry, I don't know why all of a sudden it becomes and this is supposed to be all. So let's graph that, So let's first graph the original one, greater than -2 and less than or equal to -5. So it's like that. Okay, let's graph the answer, okay? -2 is right there, -2. It says x is less than or equal to -2. That means right there, but less to the left. Or x is greater than 5. So 5 is here, greater than 5. I hope that you do see that these two are like opposite of each other, right? So therefore we have a correct negation. All right, the last term is the tautology and contradiction. So the tautology denoted by T, which is a statement always true, always true. And we do, here's one example of a statement always true. So like P or not P, because one of these has to be true. So therefore the result is true. So like, give you one example. It is raining now, or not raining now, right? Not raining now. So you say this is for sure it's true. So this is an example of tautology. And a contradiction, oftentimes denoted by C, which is the C, is a statement form that is always false. Like this is one example. And if I use previous one, it is raining now, and at the same time, it is not raining now. This is certainly ridiculous. This is not gonna happen. It cannot raining and not raining at the same time, right? So therefore, this is always a contradiction. And theorem 2.1.1 in the book provides us a list of logical equivalences. So for instance, let's quickly skim through some of those. Like P and Q is equivalent to Q and P. How do you prove that? Construct the truth table. And this is actually pretty intuitive. P or Q is equivalent to Q or P. Now, associative law means P and Q parentheses and R. You can switch the order of the parentheses. You can regroup them. When you have both or, you can regroup them in any way you want. The distributive laws, this can be a little maybe new to you. So P and the parentheses Q or R, you can distribute this in here and keep the or, okay? So similarly, you have another version for or and then n inside parentheses. Identity law, P and the tautology is equivalent to P. P or contradiction is equivalent to P. Negation law is P or not P is equivalent to tautology. P and not P is contradiction. And double negative, not P is equivalent to P. So I encourage you to read through that, and then this table should not be memorized, but you should get yourself familiar with all these rules. So skim through it a few times, I would say. Yeah, and the very last one, prove that this statement form is equivalent to P using the result from this chart, okay, from this chart. And of course, you can use a truth table, like construct truth table for this one and compare the truth value with the P and then make sure that they're identical. They're supposed to be identical. I will encourage you to do that yourself, but I'm gonna take advantage of these results to establish the equivalence of these two statements. So the first one is, let's begin with left-hand side, P and not Q, or P and Q. Okay. Now, if you look at that, I see that PM, PN, they're both the same. And here, not Q and Q, they are negation of each other. I actually, because I skimmed through a few times and this table, and I do know, I'm kind of familiar with this chart, okay? So therefore, one of those two will be applied. So I will challenge you, which one should be applied, right? I hope that you see that this one can be applied, right? This one can be applied. So apply that. So by number 3, it becomes, so we begin with this side. So it becomes P and not Q or Q, okay? So this is by the rule number 3. And now this one is by number 5, this rule. This is the negation law. This is equivalent to a tautology. So therefore, this is P and a tautology. This is by number 5. And P and tautology, right there, P and tautology. Let me try to look it up right there. Actually, right there, P and tautology is P by identity law. This is equivalent to P by number 4. I hope that you see that the advantage of using these results, it is much, much shorter. Otherwise, you construct truth table, which can be a little tedious, but it's certainly doable. So this concludes the section 2.1